You can have high power actuators, you can have low power actuators, you can have even smaller power actuators. So if you have like something like some MEMS kind of actuators, they are also available nowadays. So you can have any type of actuators based on how power requirements are. And also you have actuators which are binary or continuous. So if you have an actuator which is like on off, for example, you're turning off a relay or turning on a relay, it is basically binary. The switch can either be on or switch can be off. On the other hand, if you have a control valve which are trying to control from a very far away place, the control valve can be open to any degree. You can have fully open control valve, you can have fully closed control valve, in between also 10% open, 20% open, 30% open. So you can continuously control the operation of a control valve. In that case, it is a continuous type actuator. All right. Also, you have an application which kind of says what is the area of application of the actuator. So in that, what we have is we look at where the requirements are, and you typically use actuators which are tailored for a particular application. If you take the example, you can use the same control valve for water and maybe for something like say some kind of fluids which are non-volatile, but you cannot use the same control valve for gases. They use a different type of control valve. So you cannot use the same type of control valve which you use for gases for controlling volatile fluids. So they are all different types of fluids, and based on the type of application you will have to change your actuator type. Okay. And the last one is the type of energy that they use. So you have, if you take the example of, say, very simple example of control valves, you find that they are actuated either by using electricity, by hydraulics, or by pneumatics, that is air. So all three types of control valves exist. So based on the type of energy they use, you can have them separate. So based on the type of actuators, you have this kind of examples. You can have mechanical, you have electrical, electromechanical, electromagnetic, hydraulic, smart materials, micro and nano actuators. So all these things are different types of actuators. Out of this, the last two that you are seeing here, smart material actuators and micro and nano actuators, they are very specialized. You will not find them being very widely used in field applications which require a lot of robustness, or the ones which require a lot of reliability. So lot of these smart material actuators are still in experimental stage. Micro nano actuators are also kind of experimental. Some of them are commercial, but a lot of it is still experimental. So you will not find a lot of them out in the field as such. But the first 5 types that you will find are very common, and you will find them being used extremely widely. Okay. Can I go to the next slide?
Yes, sir.
Okay, so here what I have given is I have just listed out showed some of the type of actuators that you will find. Some of them are very kind of, I will say, familiar to you. Some of them may not be that familiar. So I'll just start with the most simple type of actuator that you can find. That is the solenoid type actuator. I'll just play the video, have a look, and see what you understand. Okay, just play this.
Yes.
Tubular solenoids are on-off type linear actuators that develop force in one direction when the wire coil wound around a metal core inside of the device is energized with an electric current through the lead wire. The current applied to the coil creates an electromagnetic field that exerts a pulling force on the iron plunger. The return force can be provided externally through a return spring, for instance. Now here's how a tubular solenoid becomes a push type of actuator. As you can see, the pulling force on the plunger translates to a pushing force with the addition of a push rod. Tubular solenoids are especially optimized for applications calling for long strokes due to their cylindrical shape and plunger geometry. G+ engineers have also created a unique actuator known as the superstroke solenoid by modifying a traditional tubular solenoid to supply cost-effective semi-proportional movement over a surprisingly long stroke. You can find a link to a short informative video on the superstroke in the description below. Have a question or suggestion for a future video? Let us know in the comments below and visit us at gplus.com, where you'll find plenty of information along with the latest G Plus worldwide digital product catalog. And don't forget to subscribe to G Plus on YouTube and follow us on Facebook.
Okay, any questions on this?
Sir, does super stroke mean that it actuates at a slow pace?
Because what they are claiming, typically the solenoid type valves are on-off type. So when you apply most of them are 24 volt or 12 volt. So when you apply 24 volts, the whole thing will shoot up and it will go to the one extreme. You remove the 24 volts, it will retract and come back to zero. So there is no in-between movements typically available for solenoids. So what these people are claiming is that they have custom-made a solution which can give outputs which are proportional to the input that you are giving. I have not seen many of them in the market. This is kind of a specialty that they claim. So maybe in this case, what happens is if you increase the voltage slowly, this valve will actually move slowly, and you will be able to get a proportional output as a result of it. But conventionally, if you buy it from the market, you will get only on-off. You supply the voltage, it will shoot up. If you just remove the voltage, it will just come back in. That's your traditional solenoid actuator. And that is the cheapest control valve you can buy also. Okay. Is it okay? Any other questions?
No, sir.
Yes. Anybody else has any queries?
No, sir.
No, sir.
Yes, if there are questions, please go ahead. Okay, so there is no question, then I'll just move on to the next slide.
Facebook and LinkedIn as well.
So next is an example of what linear actuators do. You have all seen different kinds of motors, right? So motors always rotate circularly. So what happens is that sometimes you do not want circular motion, you want linear motion. So when you want linear motion, what do you do? So for linear motion, you have linear servos and linear actuators, which can kind of give you an output, which kind of moves the actuator uh, rod in front and back based on the amount of voltage that you give or based on the control signals that you provide. These kind of movements, yes.
Sir, I have doubt from the previous one. Solenoid.
Go ahead. Go ahead. Go ahead.
Sir, if there is no spring at the end, will it stay at the same place even after the supply is stopped?
That is the problem. Typically, what happens is that if you don't use the spring mechanism, it will stay there. There is no way in which it will come back to its original position.
Sir,
So most of Go ahead.
so if I change the direction of the current,
No, it does not happen like that, because see what is happening is you have a there is a coil which is wound around it actually. So based on the coil winding, there is a force of either attraction or a repulsion. So when you have this energizing of that coil happens, the force, electromagnetic force, actually pushes the solenoid, that rod that you are seeing outwards. And because of the electromagnetic energy, it kind of stays there at that position. As soon as you remember it, it will retract back into that place where the coil is existing. Because if that was not there, the what do you say, that the rod would have actually come out of the field of the coil, and then there will be nothing to push it back in. I don't know if it makes sense to you.
yes, sir, yes, sir.
So that is why they use some kind of a spring to bring it back. It's always spring loaded most of the times. So in case of linear servos, that is not the problem. You usually have rack and pinion type arrangement in this, so you can convert that circular motion of motors into linear motion and so on and so forth. So we'll see some of that in this video.
Hey guys, I'm Kyle, and this is Jason. Today we're going to talk to you about linear actuators and linear servos and different ways to operate them. So for starters, I brought in a linear actuator. We're just going to supply power from a 12-volt battery to this and watch it run. So you'll notice I've got a huge lawnmower battery here. You don't have to use one of those. You can use a small LiPo pack or a power supply or about anything that's going to supply 12 volts to it. So Jason, if you want to hold that up, basically
I'll pause it now. Remember that they are also saying that you have to either use a 12 volt or 24-volt battery. So for almost all of these things, which these are simple actuators which are controlled by DC. Okay, so you can directly power them with the help of batteries, and you will either be using 12 volts or 24 volts.
I'm just going to connect power to the motor. It's going to run out until it hits a limit switch, and then it's going to kill power. Once it's hit.
Next important thing is the idea of a limit switch. Okay, in most of the control valves, in most of the motors, especially in linear actuators, you have a separate device which is called a limit switch. Okay, so the limit switch is when the actuator rod has extended to the maximum limit. It hits a hardware switch which is built into the system, and when it hits that limit switch, the power gets automatically cut off. Otherwise, what will happen is that this motor that you are seeing here will try to continue to run, and it will push this actuator out. And since there will be some kind of a physical block here, the actuator will not be able to move. The motor will continue to run, it will get loaded, and eventually this may get overheated and damaged. So that is why you always put a limit switch somewhere here, so that when the shaft has reached an extreme limit, that limit switch is triggered and the power supply gets automatically cut off. Okay, so there will be two limit switches in many cases. One will have this kind of a distance kind of a limit switch, position limit switch, and the second one will be the torque limit switch. So if the motor that is powering the linear actuator kind of is subjected to a torque more than what it can handle, you will have an over torque limit switch which will automatically cut off the motor also. So this is what sometimes you may experience when you are using a ready-made kind of motor assembly to run some heavy duty equipment. When the torque becomes too high, the motor may automatically cut off, and you will be wondering why the motor is getting cut off. The motor is getting cut off because its torque limit has exceeded, and that over torque limit switch has been activated. So that is the two kind of actuators that you will limit switches that you will be experiencing or dealing with. Okay, limit switch, LIMIT, limit switch.
Hit the limit switch, it's not pulling any current, so it can sit there for a long time. It's not going to drain your battery. When you're ready to run that back in, all you got to do is reverse polarity to the motor. I'm going to switch it at the battery, and it's going to make the motor run in the reverse direction until it hits the inboard limit switch. So that's about the most simple setup that you can get with a linear actuator. So let's say you want to run this on an application like a dump bed on a UTV, and you want to run that off of a switch. That'd be pretty simple to do as well. All you need to do is supply power to the switch and wire the actuator in. And what you're going to need is a dual pole, dual throw switch, is BPDT, and you can get a momentary or non-momentary version. So if, for example, you wanted to flip the switch all the way down, make it run out and hit the limit switch, or flip it all the way up and make it run in without holding that switch in position, then a non-momentary is what you would need. If you want to actually have to hold that switch in place to make it run, and whenever you release the switch it pops back to center, then you'd want the momentary version. So those are the pretty simple options. I'm going to let Jason talk to you about some of the more complex options to get more functionality out of the linear actuators.
Right, so those options work great if you don't care about speed control. And for a linear actuator application, you might not. But there might be a situation where you want to control the speed throughout the stroke. So in that kind of scenario, you're going to want to have some sort of motor controller. So any motor controller that can drive a 12-volt DC brushed motor would work great for these linear actuators. In this particular case, I've got a 12-volt linear actuator here connected to a Activotics dual motor controller. And it's worth noting that in this first example, we're only using the black and red wires because those are the wires that are going directly into the motor to run it forward and backwards. And I'm going to be in RC mode or mode 1 on this motor controller, so that it's going to drive the motor based on the signal coming in on the input 1, and that's going to be listening for a PWM signal like you'd get from an RC receiver, or like you could output from an Arduino or some other microcontroller. So I'm going to go ahead and connect my little LiPo here. And this is controlling the speed and the direction as I turn the knob here. And I'm just using the Activotics manual dual servo driver to create that PWM signal. So essentially this is just a slightly more refined version of that, where you're just driving the motor back and forth, and the thing you gain here is you have speed control as you do it. Next, I wanted to show if you were to take and utilize the other 3 wires that you have here, you could have feedback as to where this is and control where you want it to be. So to do that, I'm first going to add some jumpers here to put this dual motor controller into mode 4, which is position control mode. And in that mode, it's going to be reading data from the pod. It's going to be reading an analog input signal, essentially, and that'll tell the motor controller where the linear actuator is within its stroke. And then it's also going to be still listening to that PWM signal to determine where it should be. So it'll look at where it is and where it should be and move the linear actuator to adjust. All right. So the thing to note here when you're connecting a linear actuator like this is you want to make sure you know which wire is which, so you want to refer to the documentation. In this case, the blue wire is the wiper on the pot, and it literally is just a potentiometer that's built into this case here that's being driven by the motor. So you saw immediately that jumped to a particular position based on where this knob was when I powered up the unit. So as I turn this knob, it's going to move just until it gets to that position. So it's going to be proportional, comparing the overall stroke to the overall rotation amount on the dial here.
So Jason here's a techie. He's talked to you about the motor controller connected to the linear actuator and the different options that it gives you. Basically, to recap on that, you have speed control and position control. Speed control, the knob position is going to determine how fast the actuator moves, while position control, the knob position is going to determine the position of the shaft on the linear actuator. So not that this is too complex, but I try to go simple on my projects. So I want to talk to you about the linear servo instead of the linear actuator. You'll notice that the body is basically the same. You know, it looks almost identical. However, the wiring is different. This already has a circuit board down inside, and it's tied to the motor, and it's tied to the limit switches and potentiometer. So it kind of does all that work for you. So all you need to do is connect this, and I'm going to switch my polarity that way. I have negative to negative, positive to positive. That's important on the linear servo. So I'm going to connect the Tamiya, and then I'm going to take the servo lead and plug it into the servo controller. It moved all the way out because my knob is all the way to one end. So you'll see that this is position control, just like the second mode that Jason had talked about. It kills power at either limit switch. On this setup, it is going to pull just a little bit of juice when setting on the limit switches because you do have a servo controller that's getting power from it. The other nice thing about this setup is this has a 5-volt BEC built into the circuit board. So we're plugging in 12 volts here. It's breaking that out. It's sending 5 volts to the servo controller, and so it's powering that as well. You only need to maintain one battery or one power source with this setup. For you visual learners out there, I'm going to go ahead and dissect one of these linear actuators. That way we can see the inner workings of them.
While he does that, I'm going to touch on some of the differences, just to summarize, between linear actuators and linear servos. So linear actuators have probably the simplest setup option. All you need at the most minimum, it would be a battery. And you can change the direction by changing the polarity of the red and black wires. While on a linear servo, you don't want to change the polarity of the red and black wires. The polarity is important. On a linear servo, if you're going to take a PWM signal to control the position, that's a much simpler setup, but it can be done with a linear actuator. And even though it's a little bit more complicated because you have to use an external motor controller, whereas the linear servo has a built-in motor controller, if you're doing a project with a microcontroller, this might be a really nice way to go because you can read that pot value as an analog input into your project, and then your program can know where it is within the stroke.
Right. So I'm going to start at the top here and go ahead and take the cover off, which is going to expose the shaft that extends out. This cover has a profile that's going to hold the limit switch rail. So you've got an outboard and an inboard limit switch, and it's held in place nicely when that's put in. And then you've got the aluminum extension tube, which is going to expose the Acme rod. It's basically a threaded rod that's nice and polished, and then it's got a Delrin nut on it that runs up and down. So as this rod is rotated by the motor, that Delrin nut is going to move up and down. And with this in place, the little finger off the side of the nut is going to contact the limit switch at either end and just kill power. So that's kind of the end of it. We'll get into the back side here. I've already taken the screws out just to save some time in the video. You'll notice there is a potentiometer, and then there's a series of plastic gears inside of here. Now, if you look at the specs on the linear actuator, you're going to notice that we say metal gears. Don't get too caught up in these plastic gears. They're just for the potentiometer, which is your position control. They don't take any torque or anything like that, so they're not going to break or wear out. They're just driving this potentiometer shaft. And I'll go ahead and cut that wire so we can get into the gearbox. I'm cutting the red and the black wire that run through this part of the gearbox, and they actually go down into the limit switches that we had talked about, because the motor is then tied to the limit switches. Alright, so once we have these taken out, you'll notice all the gears, and these are the gears that actually drive the system. So you've got these metal gears that mate to, there's actually a plastic pinion gear on the motor, just because it's very high speed. The plastic pinion is not going to take much torque at all. It just needs to spin very quickly in order to drive these. And so each gear in here is going to step that down, slow it down, increase your linear thrust coming out of the actuator, and then you get your plastic gear on top that is going to drive the potentiometer assembly that we had talked about. So if you break it down and look at it this way, it's fairly simple. It's just a DC motor running a series of gears, and then you've got a potentiometer for feedback if you guys want to use it. If you're just running on a switch or just running on battery power, you don't even need to use those 3 wires. Well, Jason and I have gone through all kinds of different ways to run linear actuators, as well as a look at the linear servo. If you guys have any questions, be sure to email tech@servocity.com. If you like the video, go ahead and press the like button. Thank you.
Okay, do you have any queries on this? Was the video completely visible to all of you?
Yes, sir.
Yes, sir.
Yeah, any
Sir,
questions?
I
Yeah.
have a doubt.
Hmm.
Sir, which is more efficient, sir? Hydraulic method or this one?
Hydraulic transfers much more power actually. So if you have a very high power application, we will go for hydraulics. Like you in your JCBs and all those things you find, no?
Yes, sir.
JCB tends to use hydraulic kind of actuators rather than electrical.
Okay, sir.
They're moving to electric now, but traditionally we have been using hydraulics for very high power applications. But again, the problem with leakage and other things are there. It kind of gets very messy. So people are now kind of trying to replace it, because now you have much higher efficiency electric motors, so they are transitioning to electric motors. Common example
Okay,
will
sir.
be the JCB machines that you see, the backhoe loaders and those kind of things that you see. They have been traditionally using hydraulic, but now I am seeing full electric JCBs, like not even diesel for propulsion, they use full electric. So even they are like it's commercialized now, so you will find them in Indian markets also very soon. There will be no hydraulics involved, no pneumatics, no IC engine, no diesel, nothing, only electric.
Okay, sir.
So we'll see that quickly. Very soon it should come to Indian markets also. Okay, any other questions? Any queries quickly? No? Okay,
Sir,
Aditya,
PWM means it fires pulses rapidly.
PWM is basically fires rapidly in the sense you set the you will have a frequency, and then you change the on and off times to
Yes,
control
sir.
the
Yes.
speed at which it is moving. Yeah, so basically most of the this is mainly to help with the control of motors using microcontrollers, because microcontrollers mostly have a PWM output, na? So to make it work better with with the microcontrollers, they give this PWM. That's the only reason. Any questions? Anything else? Okay, so if there are no further questions, can we go to the next slide? Please do ask. There are a lot of things that kind of would have appeared new to many of you people. So I just wanted to find out if everybody is understanding it or if there are any queries. They mentioned a lot of things in the small video that you have just seen. Anything? No, okay. Fine. So we'll go to the next slide. Let's see. Next is this. So we are going to have a look at very simple idea of what is a pneumatic cylinder. I will not go into Arduino. You already know all these things, but we'll have a look at what is a pneumatic cylinder. So there are several cases where you may not be allowed to use linear actuators, especially where you are looking at industry where you have volatile compounds. So if you have anything which is kind of volatile, like say in the paint industry, or if you're trying to say work with chemicals such as alcohol or something like that, they are very volatile, and they are likely to and inflammable. So if you have things which are volatile and things which are inflammable, you do not want them to be in the presence of electricity, because a small spark can actually ignite a very large fire. So the best option will be to use pneumatics in those conditions, and that is why you will find that in many industries people would still prefer pneumatic type of actuators. Okay. And also because they are the only things which are allowed by the NEMA standards. So you have this NEMA standards which kind of specify zone regulations, and they tell you that you will only get the certifications or the license to operate if you satisfy certain criteria. So for certain zones, you do not have an option but to use pneumatics, because otherwise the health and safety and the fire and safety people will not give you license to operate. Okay, so in those cases, you have to either use hydraulics or you have to use pneumatics. And because pneumatics is much cheaper when compared to hydraulics, you tend to use pneumatic type actuators. So we'll just have a look at what pneumatic type actuators are. And unfortunately, the problem with pneumatic actuators, as you can already guess, is that it is very difficult to control them precisely. Electric actuators you can control precisely with the help of PWM or with the help of digital inputs. You know exactly where you are going. If you have a servo, much easier. But it is very difficult to do that with pneumatic actuators, because controlling air pressure exactly to the limit that you want and to make sure that the diaphragm which is actually pushing the final actuator out should move in exactly the same way is very, very difficult. So you will find controlling a pneumatic type actuator to be far more difficult than controlling a electric actuator. And that is unfortunately the reason why pneumatics are kind of falling out of favor in the modern era, where the people tend to push more for actuators which are electric, because you get much more precise control. Okay, so let's go and see.
Hey, what's up? It's Triggy, and today we'll be controlling a pneumatic cylinder with an Arduino. The whole point of robots is that they move. The most typical source of movement comes from motors, which convert electrical energy to rotational motion. Sometimes we want to move linearly, though, instead of spinning. A common solution is to use a linear actuator, which, by the way, is actually just a motor spinning an Acme rod, and like motors, linear actuators can be made very precise and can be powered electrically. The trouble is they're not all that powerful, meaning they're not really that fast and not really that forceful. You can trade off force for speed and vice versa, but you're still very much limited by the overall power output. So, for cases where you need speed and power and not so much fine precision control, consider pneumatic cylinders for your project. A quick refresher on pneumatic cylinders. Here's a cross-section of a cylinder. When air is applied to the left input, the cylinder rod is forced to extend. When air is applied to the right input, the rod is forced to retract. We can control the flow of air into the cylinder with a 5-2 control valve. It takes a single stream of air as an input and controls the airflow through the two outputs. It also has 2 exhaust outputs to control the flow speed of the air out of the cylinder and thereby the speed of the rod. Here we'll add some Teflon tape to quick connect fittings. A fun fact about building stuff in the US is that not only do you have to be comfortable with both metric and imperial units, you also need to buy whack parts to convert between them. For example, the threads here are 1/4 20 to match the air compressor, while the input for the tube is 6mm to match the cylinder. Now that we have all the connectors and exhausts attached, we can look into how the airflow is controlled. The electrical terminals are tucked away in here, so we can unscrew the sections to access them. When we apply 12 volts to the terminals, a solenoid activates and air flows through one of the two outputs. Let's call it output 1. This makes the cylinder rod extend. When no voltage is applied, the solenoid is not active and air flows through output 2, and the rod retracts. So all we have to do is apply and not apply 12 volts to the valve to control the cylinder. Here we can hear the solenoid clicking when I attach and detach the battery. Let's cut some 6mm tubing to connect our input to the control valve, and the valve outputs to the cylinder inputs. Now we can power up our air compressor and connect it to our system. We haven't worked out any of the electrical stuff yet, but the control valve has a test button which we can use instead of the solenoid to activate the cylinder. And it looks like everything's working so far. But we don't want to have to press this button constantly, we want to control the cylinder with a microcontroller like an Arduino. To do that, we'll use a transistor. This one is an FQP30N06L MOSFET. This will act as a switch that we can control with a 5-volt signal. If we apply 5 volts to the gate pin of the MOSFET, we allow current to flow. We'll power one side of the breadboard to 5 volts with the Arduino's 5-volt and ground pins. We'll then attach cables to the other half of the breadboard, which will later connect to a 12-volt power source. We'll also tie the grounds together. We'll then connect a signal wire between the gate of the MOSFET and one of the digital output pins of the Arduino, let's say pin 5. We'll add a pull-down resistor to the gate, then add indicator LEDs to the 12-volt source, the 5-volt source, and the gate. This will help us keep track of what our circuit is doing in action. We'll then connect output cables between the 12-volt rail and the MOSFET drain pin. This is the output and will connect to the control valve solenoid. And that's it! The 12-volt indicator LED turns on when we connect 12 volts, and likewise the 5-volt indicator LED turns on when we connect 5 volts. Let's write a super simple script to control the behavior of the cylinder. We'll assign our signal pin to be pin 5, declare it as an output pin, and then alternate between setting the pin high and low with a 1-second pause in between. Let's connect the battery, the Arduino, and the solenoid to the circuit. If we touch the signal pin to the 5-volt rail, we see the blue LED turns on and the solenoid activates. If we connect the signal wire to our output pin, The LED and solenoid activate at a steady rhythm. Let's attach the cylinder, connect the pressurized air, and connect the signal pin to our output pin. We see our cylinder extends and retracts exactly as we specified in the code. And now we have successfully controlled the behavior of a pneumatic piston with an Arduino. Fun! That's it for this video, thanks for watching. If you enjoy this kind of content, be sure to subscribe, and I hope you liked the video.
All right, any questions on this one?
No, sir.
The only requirement is that you will need to have a compressor, air compressor for your applications. We had one in the process control lab. We have a complete set of equipments, but I don't know if it is still available. So if you have time, please have a look at the process control lab that we have, and you will find some of these things that I have mentioned being used there. Okay, so it is very useful if you need to use high power devices or places where you cannot use electric motors or machines. Right. So let's go to very quickly to the next
Hey, what's up?
lot. We're going to thyristor. Or what I will do is I will continue with this in the next class. It's already 12:47. So we'll stop with this for now and we'll continue in the next class. So meanwhile, if you have any queries, please go ahead and ask. Any questions so far?
Sir.
No. Okay. So are you people okay with the idea of actuators? Your motors can be actuators, anything can be an actuator, but these are relevant from IoT viewpoint also. Why? Because you may sometimes require not just measurement but also actuation from a remote location. So that is where these kind of things come in handy. Okay. Any questions, please go ahead. I think we have like 2 more minutes to go. If you have any queries, please go ahead and ask. Anything?
No, sir.
No. Okay. Fine. So if there are no further questions, I think we will break for now. I'll share the presentation with you very soon, and we'll continue in the next class. Okay. Thank you all for attending. Bye.
Thank you, sir. Thank you, sir.
Thank you, sir.